Welcome back to Nature of Code in Rust and GGEZ. In this video, we're going to be going over example 2.5, fluid resistance. So this is slightly different than the coefficient of friction, the friction that we did previously, although it's also similar in a way. Let's take a look at this example here, which is we have these movers that all fall at the same rate because of gravity, and we have probably a frictionless environment at the top, and then we have some kind of liquid. It could be air, it could be anything. Air does act like a liquid in real life, and that causes drag to happen once it hits the bottom, which is why you see different masses move at very different speeds. So that's what we're going to do with Rust and GGEZ. All right, so first things first, let's go ahead and make sure that we've got a bunch of circles being created and that they are all they're spread out across the arena here. So we know we're gonna have a bunch of movers. So we're gonna have our movers here, a vec mover, and let's go ahead and create a bunch of these. Now I'm thinking we can have them have a variable amount of mass, and if I remember correctly, in mover, our mass is exactly equal to the radius. So we'll just keep that in mind here. So let's actually create let's set up a random number generator for ourselves. And now we can loop through, let's make like 10 of each. And if I want 10 of them and I want to spread them out evenly across the arena, I'm going to need our width. So that way I can get like our size, figure out exactly, how like the space between, that's what I need. So let's go ahead and get our width and height. So we'll need the context here. And then we can calculate our space between. So we're going to have, let's just say 10 of these. So space between is going to be equal to our width divided by, let's choose do 10. And that should be fine for right now. Now I want to loop through and create 10 of them. So I need a count from, let's do from 1 through 10 inclusive, and that way I can use the 1 to multiply by our space between, so it gives us a little bit of room on the left hand edge for that the left mover. So do a 4, let's do a count in, instead of 0 it's going to be 1 dot dot. Now normally ranges are not inclusive, they're exclusive, so I can do an equal sign and then now it's inclusive for the right hand number here. So it's 1 through 10, including 10. Okay, so we can create our mass now. So let's do that. We're gonna use rng.genRange, and I want some, let's have maybe let's do 5 as the smallest, and let's do maybe 30 as the largest. And really it's 29.9 because this is non-inclusive for that 30. Okay, so that gives us the mass here. And then I think we can just go ahead and create our mover. Okay, so we need a location. So that's going to be our vector 2. We need an X and a Y position. Our X position is going to be starting with the count. So count, we're going to multiply the space between, and then we're going to add the mass. And because we remember that the mass is a 1-to-1 ratio with the radius, so that should be fine. And then for the Y here, let's just bring it as mass, so it starts near the top but not above the top. And then, okay, our mass, well, there we go. There's our mass, and we have our mover. So we do need our movers. And we'll just push this mover straight on in here. All right, let's see. What are you upset about? Cannot multiply an integer, right? So count is an I32 right now. I can't actually make these F32s because we can't iterate through F32s in that way. It just doesn't know, Rust doesn't know how. So we'll just convert this into an F32 at this point. All right, so then I want to draw these out. We don't have any physics applied to them, but we can see them across the screen, make sure they look appropriate. So we're going to do our standard sort of like draw system here. So let mute. We have our mesh builder. Then we're going to take this mesh builder and apply it to all of the movers. So that's just going to be a simple for loop. So for mover in a reference to self.movers. Once we have that, we can create our mesh. And then draw it out. And I think this should be enough for us to get a bunch. Let's see, what are you upset about? Oh, when we build, we have to question mark. That's what I'm forgetting. All right, this should be enough for us to see all of our movers at the top of the screen. And there they all are. They're not exactly at the same sort of like, well, I guess they're starting. They're not the exact right height. They're not even. So let's maybe, we know that the highest they could be here is 30. So let's just make the y 30. And then that should make them all have their centers in the same spot. There we go. Now, if I want to create a gravity and apply it to them, let's go ahead and create a gravity here. So we're not going to have gravity move it sideways, just going to be our y, and that's going to be, let's just say 0.1. I think we've used that in the past. And we're going to apply the gravity to the movers in here. So for mover in immutable reference to self.movers, we're going to apply force self.gravity. So if we run this now, well, applying the force is great and all, but we also have to update it, don't we? So we have to go mover.update. That will actually cause the forces to move the balls. And we notice that they're not falling at the same rate. Well, that's because we have mass is affecting the balls here. So before we can create this gravity like this, we're going to get a copy of gravity. So let's do move gravity, self.gravity. Once we have this gravity, let's go ahead and multiply it by the mass of the mover. And then we'll apply this custom gravity. And now they should all once again fall at the same rate. There we go. Okay, well that's great, but they fall right through the floor. So let's go ahead and update mover so that our check edges causes them to bounce off the bottom of the screen. which means we need the screen. Let's just go ahead for future updates, make this easier on ourselves. We'll just do, this is the, maybe like screen width, screen height is a tuple of F32 and F32. And then here we're going to do if y, and then I want the bottom to be bouncing off of, well, the bottom of the screen. So if self.location.y plus self.radius, if that's greater than screen height, then a couple things. I want to reset our location so we don't like clip through the bottom and then do this weird jittery dance down there. Self.location.y, set this equal to screen height minus self.radius. And then we're going to not totally reverse the velocity, but we're going to reverse the y of the velocity. So self.velocity.y times equals -1. And then if we run this check edges, so let's do it after our update. So that'll be mover check edges. We do have to get our drawable size. Let's just do that once at the beginning of update here. So let drawable size equal, and then this gets replaced with that drawable size. Not drawable size. There we go. So now if we run this, we should bounce off the bottom. Okay, so far so good. It does sort of move at the same velocity up and down. That makes sense. We have a zero friction and zero drag environment right now. So now we're going to want to add the liquid, add the ocean, as it were. So we have this zone here. We can make a little bit of changes here. So instead of coefficient of friction, this is going to be coefficient of drag. And we've also noticed that we need to make maybe the coefficient of drag public, and we need the height public. The reason for these to be public is because instead of applying a friction to mover, we're going to delete this code. We're going to follow the example of the book where the mover is the one that applies the drag from the zone that it's in. So if we come over to the mover, we need to, well, a couple things. We need to check to see, are we inside the zone? So pub function is inside the zone. That's going to take just a reference to self, and then we also need the zone, which is a reference to the zone. And we're going to return a Boolean. Now, I'm going to make this super, super simple. We just have knowledge that our zone is the entire entire width of the arena. So if the y is past it, then we know that we're inside of the zone. If this is like maybe smaller pockets that some of them would hit on their way down, then we'd also have to check our widths to make sure that, hey, are we to the left of it? Are we to the right of it? And so on. But it's going to be a little bit easier here. So we're just going to say if self.location.y plus self.radius. So if the bottom edge of us, if that's greater than the zone dot y, oh, so we need the y position also. So actually, I don't know if you need the height. I think we just need the y, because we're going all the way to the bottom. So this is what it is. If the bottom of our mover is lower than the top of the water line, then we're in. So return true for this. And then once we know that we're inside the zone, we want to apply drag. So pub function apply drag. So we're going to have a mutable self And then we're going to have the zone, which is also a reference to the zone, and we don't need to return anything. So what is drag in this case? Drag is similar to friction, but there's just a slightly different algorithm to calculate it. We're going to, we have to get the speed of the speed that the mover is going to the power of 2, and then multiply that coefficient of drag. So I guess let's start with that. We're gonna get let the the speed that's gonna be equal to self dot velocity dot magnitude. Okay, so that gives us that. Then we're gonna have like a drag speed, and drag speed. What am I doing? Drag underscore speed. Snake cased. Drag speed is going to be equal to this speed to the power of 2. And then we're going to take that and multiply the speed. No, not the speed. The coefficient of drag. So that's the zone dot coefficient of drag. Okay, so that gives us our drag speed. And then we're going to get the velocity again, and this is going to be the actual force. So that mute, this is going to be the drag force is equal to self dot velocity. So we're going to get a copy of that. We're going to reverse it. So drag force, we're going to reverse it. Then we're going to normalize it. Force dot normalize. Now it's been normalized. We're going to multiply it by this drag speed. So drag force times equal to the drag speed, and then we can apply it to this mover. Apply force, and this is going to be the drag force. All right, so we have this inside zone and apply draw. So let's head back to the main library, and after the gravity, let's go ahead and do this. So if mover dot is inside zone, and we'll give it a reference to self dot. You know what? We don't have the water, do we? So we can't actually do this yet. Let's go ahead and create the water. So we have water, and that is going to be a zone. So that water is going to be equal to a zone new. Okay, so where is it starting? It's going to be across the entire screen, so 0 to 0. And let's also make sure this is halfway down. So height divided by 2. Our width is the entire width, and our height is half the height. Then our color, let's make this a nice blue maybe, because it is water. So we'll do 0, 0. We'll do a full blue, and let's do like 0.3. Something, see-through across black. It won't be super bright. It'll be nice and dull. And then our coefficient of drag. I don't actually know what would be a good thing to set this to. Let's just set it to 0.5 and sort of like see what it is. That gives us our water, and let's go ahead and store this away. And I want to make sure that we draw this. We already have that draw method there, so we should be able to, before we build this, self.water.draw and pass it an immutable reference to the mesh builder. So if we run this, it won't apply that drag yet, but we should see the water there. Okay, everything works as expected. The next thing we want to do is now apply that drag. So here's where we apply the gravity force. We're going to do if mover dot is inside the zone, a reference to self dot water. So if the mover is inside of water, then go ahead and apply the drag. So that's going to be mover dot apply draw. Apply drag. Okay, so apply drag and pass it a reference to self.zone, self.water again. And that should be enough to apply this drag. Let's see what effect this has. It hits the water and immediately slows down, and everything starts getting affected by the mass again. And that's pretty much exactly what we see in the example from the book. So anyways, this is example 2.5, fluid resistance. Thank you so much for watching. I look forward to seeing you in the next video. Have a great day. Bye.